this works. Aha, okay. So I'm sorry for everybody who's been waiting on the YouTube stream, but I think we've actually made it to be live now. And we had some technical issues with the live to YouTube streaming, but I'm very, very happy to have Andreas Geiger speaking with us today in our 3DGB seminar, along with guest panelists Eustace Thies and Karsten Roeder. So Andreas is a professor of computer science at the University of Tübingen and the MPI in Tübingen, and he's done some really foundational work in terms of robotics and autonomous systems, and especially in terms of the KITTI data sets and advances in terms of semantic perception and exploration, and recently done some really amazing work in terms of neural implicit representations and how to understand 3D representations with these new implicit representations. So Andreas, I think you can start.
Thanks, Angela. Welcome, everyone. A little bit delayed. I'm trying to make up for it. And thanks, Karsten and Eustace, for joining as well. So yeah, so we are interested, my research group is interested in vision for robotics in general. And one key aspect of robotics is, of course, 3D vision. Right? So we need to reconstruct the environment. And one of the most traditional 3D reconstruction approaches is as follows. Given a set of images, we want to maybe first extract the camera poses, and then we want to find dense correspondences. And from that, we can get depth maps that we can fuse together into a more coherent reconstruction, where we can then do some mesh level refinement, add some semantics to it, etc. So this is a very traditional 3D reconstruction pipeline. However, humans recognize 3D. Important aspect of our perception. Those robots that are really intelligent and can interact with the environment, we also have to put them with this kind of perception. So can we learn to infer 3D image? One of the
Hi, I'm very sorry to interrupt, but I think there's something, we lost your sound like a minute or two ago, or it's very, very low volume. Is it still low volume? Getting better, yeah.
Okay, trying to crank this up a little bit. I can also go closer to the microphone if that's a problem. Yeah, just interrupt me if there's any. It's okay now?
Yeah, sounds good.
Okay, thanks. So that's the setup we're going to consider. And so, of course, it's kind of clear what's the input representation. We're dealing with 3 images, so we can use rendered confidence to process them. But what is a good 3D output representation? And that's something that we have been working on for a while now. So in the context of deep learning, like using a neural network to predict from an input image to a complete 3D reconstruction, there is basically 3 representations that people have considered: voxel-based representations, point-based representations, and meshes. And while all of them can be used as output representations for deep neural networks, they are all limited in the sense that they have to discretize space. So voxels have to discretize space by creating these little cubes. Points are discretizing space into point sets that are not connected, using topology, and meshes are discretizing into vertices and faces, and are actually quite hard to predict as an output representation for deep neural networks, unless you have a already well-aligned template mesh that you just have to deform a little bit. We were wondering, well, is it actually necessary to use a explicit discretized 3D shape representation, or can't we just represent the 3D shape implicitly, but not implicitly as in the sense of building a discrete voxel volume where we store a signed distance function, but really continuously in space. And so instead of representing the 3D shape explicitly, what we do here in this VPR 2019 work and also current works that also appeared at the same conference is we consider the surface implicitly as the decision boundary of a nonlinear classifier. So here's a function f that's a neural network that's parameterized by these parameters theta, and they take a 3D location as input and a condition, let's say an image, and then predict an occupancy probability. If that point, that 3D location, is that inside the shape or is that outside the shape, given that particular image condition. Angela, is my sound good now? Good?
I think it's good, especially when you're closer to the mic.
Okay. So here on the right are two examples. 2D, 3D, there's a linear separation here between the red points and the blue points. And here,
I think I jinxed it. Actually, it's a little bit iffy now.
My sound?
Yeah.
Okay. So let me. I'm not sure. Let me try to. Stop the sharing. I'm gonna move to another device. Because I tried something new today and that was probably not a good idea. So.
All right.
Let me see if the if Zoom is somehow regulating this sound or not. Yeah, it should be. It says automatically adjust. Can you hear me?
I can hear you now.
Okay, is that better than before?
I think so. It sounds good.
Okay, let's give it another try.
Very sorry for all the technical issues.
That was on my side. Okay, so we have a separator here between, but please speak up again if there's any more issues. We have this separator that's represented as a level set of this neural implicit function that predicts an occupancy probability, which tries to separate these blue and these red points. So how do we construct such a function? Well, we need a neural network that takes, on one hand, these 3D points as input, and we can process many of them in parallel, in this case, t points. And it also takes as input a condition, like a 2D image or a point set that we want to complete, or a coarse voxel grid that we want to make, from which we want to predict a more fine-grained 3D representation. And the way we do this is we use a straightforward residual network multi-layer perceptron. Here, these are 5 of these yellow boxes that are stacked on top of each other or behind each other. And then we inject that information that is encoded into this global feature vector here from the condition at multiple locations in this residual network using conditional batch norm. And then the output is an occupancy probability for all of these let's say 2000 points that we can process in parallel. So we have dimension 3 here because these are 3-dimensional points, and we have dimensionality 1 here because we have just a single number per point. Now we can train such a network in a straightforward fashion by just phrasing this as a classification problem on these supervised 3D points. But then at inference time, of course, we don't get the mesh directly out from this. And so what we do is we build incrementally an octree by querying this occupancy network. So here we have at a certain resolution, we are querying these points on a regular grid. And then if a point is inside and neighboring points are outside, classified by this neural network that we have trained now for this particular test image, then we mark these voxels as red. And then we further subdivide the voxels into a finer resolution. And then we query at that finer resolution if the points are inside or outside that shape. And then we can repeat this process n times until we have reached the resolution that we're interested in. And then we can use margin cubes to extract the mesh from that. Okay, so here's some results of how this works. This is a 2D input image. We have trained this model on various ShapeNet categories. Here are some baselines. The goal is always from a single 2D image that hasn't been part of the training set to predict a complete 3D shape. And you have seen some of the point and mesh-based baselines. And here, this is the result of the implicit model. Of course, the nice thing about these implicit models is that they can handle arbitrary topology because they don't directly represent a mesh, but the mesh is extracted at inference time. And here's an example where we try to, from a very sparse and noisy point cloud, go to a complete reconstruction of that point cloud in terms of a mesh. Here are some baselines, and this is the result. And we can use this model not only as a model that goes from an image to a 3D mesh, but we can also, given a set of 3D objects, we can also learn in an unsupervised fashion a generative model using a, for instance, variational autoencoder like formalism. And then we can look at the latent space, and here you can see some latent space traversals where we interpolate between shapes. And these shapes that you're seeing here are not part of the training set, of course. So this was quite successful, and the paper had quite some impact. And we wondered, well, can we do more with these representations? This was just about fully supervised learning of 3D geometry. Can we also learn about appearance? And it's actually quite simple to adapt this model to also learn about appearance by just inputting not only a 3D point, but then also conditioning on the 3D model, a CAD model, or a 3D model that was predicted by an occupancy network, and a 2D image, which is the image from which we want to basically take that texture and put it onto that 3D model. And the model that we have here is called a texture field, because for every 3D point tries to regress not to an occupancy, but now to a RGB color value. And this is actually, it turns out that this is a very good representation also to compress like compressing geometry, compressing texture. So you can compress texture with this representation much better than using just a naive voxel-based representation, for instance. So here are some results of this. This setup is similar to the one that I showed before, but now we have single image texture reconstruction where the input is also 3D shape. And so a simple 2D novel view synthesis baseline doesn't do very well from a single image, but the texture field, of course, is automatically 3D consistent because it predicts the color in 3D. So it will be automatically 3D consistent. So this is on the ShapeNet data set where we have rendered images used as condition here. And we have, of course, also full supervision. We can also do this for real images. So here we have a CAD model, and we want to texturize that CAD model with by observing a real image. And we can also combine this with the occupancy network by building a pipeline where we first predict the shape. This is the shape from the occupancy network. And then we can use the texture field to predict the texture for this unseen shape and appearance for this unseen object here. As always, all of these models have been trained on a lot of examples from different object categories. And then there's a new test image coming in, and the prediction is for this new test image. So this was about shape and appearance, but can we actually also, and there's a follow-up work that we have that's called surface light field that I don't have time to show now, but it's basically extending this representation to also predicting like a view-dependent appearance. So now the next question is, well, can we also represent object motion? Right? This was all static. And it turns out that extending this idea of implicit representations from 3D to 4D is actually not as easy because of the curse of dimensionality. So here, what we do instead is we represent a shape in 3D at only a particular time instance, t equals 0 here, for instance. And then we represent this vector field. This is now a 4D representation that we have to predict with such a velocity network. But the advantage of predicting this here in 4D is that it is not as discontinuous as predicting shapes over time. So we have a very smooth field, and that's again relatively easy to predict with such an implicit representation. So we're predicting shape at one time instance, and then we're predicting a motion field. And because the relationship between a 3D location and the velocity is very simple, it's just given by a simple ODE, which says that the location, derivative of the location with respect to time is the same as the velocity at that location. And because this ODE is differentiable, we can then backpropagate through the entire model. So here's an example. Here's an input condition, let's say an image or 3D point cloud, and we have these two networks here that can also have shared parts. One is predicting the occupancy at time t, and one is predicting the velocity at every point in time. And these are parameterized, so we want to update these parameters. And then we have this point here on the, like this is an observation. So we want to minimize the reconstruction error. And what we do with this point is we take that point at the time instance where this measurement has been taken, and then we propagate it through this velocity field by solving the ODE. You can see how this space deforms and warps here. And then we are looking at the occupancy that the occupancy network predicts at that particular time where the occupancy network is valid. And we're trying to minimize that reconstruction error. And because we can backpropagate gradients through this entire process here, we can update the parameters of the velocity and the occupancy field jointly by just observing basically 3D shapes. And one particular advantage of this method is that while no correspondences, while correspondences can be used if they are available, they are not needed. So all the results I'm going to show now are not requiring any correspondences between surface points across time. We are just requiring for different time instances where we need to know just the time, we need to know the shape, right? But no correspondences across time. The correspondences are automatically established by the smoothness properties of this neural network because it's a simple solution to basically do that. So here you can see an example where this is basically the task of predicting from a sparse point cloud the shape over time. And the naive 4D occupancy network doesn't do very well because of the curse of dimensionality. This is a points generation network, and this is the output of this occupancy flow model. Okay, so like all of the previous approaches, so I'm trying to now relax more and more of the assumptions that we have been using. All of the previous approaches have been assuming that we have full supervision in terms of for every, like for points that we can sample from the volume, we can always query if that we know the ground truth, if it's inside or outside the shape, right? So we have 3D supervision. Now, for related representations like meshes and voxels and others, people found ways to build differentiable neural renderers, which allowed to learn these representations just from images. And so we're wondering if this is also possible for these implicit representations. And it turns out that actually this also simplifies the model. So this is just the model here first. We have, again, an encoder that produces from, let's say, an image, a global code. And then we have a set of 3D points that we pass through such 5 ResNet blocks as before. But now we have 2 shallow heads, one that's predicting for every of these points the occupancy, and another one that predicts the RGB color for every of these points given that particular condition that the encoder has produced. And now, of course, the question is, how can we train this model just from images alone? And in order to do this, we need to define the forward pass and the backward pass. And the forward pass corresponds, of course, to rendering. This corresponds to the image formation process. So how is the image formation process happening for these implicit models? That's actually quite simple. What we do is we go through all the pixels. So this is an image plane here. This is the camera location, and here we see the surface. So we go through all the pixels, and then for every pixel, we find the surface point p hat along the ray that corresponds to that pixel W via ray marching. So we march in equidistant steps, and once we found that we pass the thresholds, the surface threshold, the level set, then we can use seconds method to efficiently find exactly the point on the surface. So it's a simple root finding. And then we can evaluate the texture field at that particular point, and then we can copy that color onto that image plane at that pixel, and then we can do this for all the pixels, and so we get the image. Right? Now, but how can we do the backward pass? How can we build this differentiable backward pass where we backpropagate the gradients through this forward operation? That's a little bit more tricky. So what we want to do, as always in neural rendering, is we want to compare the prediction here at the bottom that is produced by the model in the forward pass to an observation. And you can see that they are slightly different here. So we want to minimize that discrepancy. And we can do that by just minimizing a standard loss function that compares overall the pixels, compares the pixel color values, let's say an L2 or L1 norm over these color values. That's what we want to minimize. So what we need to do is we need to compute the gradients of this loss function with respect to the parameters of the texture field and the occupancy network, which I'm just denoting by theta here. I'm using the same symbol for both. So of course, this is simple, the chain rule, the loss with respect to the predicted image and the predicted image with respect to the parameters. And the predicted image with respect to the parameters is this expression here, because the predicted image with respect to the parameters depends on the parameters not only through the texture field, but also through the surface location that we have found through our root finding procedure. Right? Now, so this is the total derivative simply. Now, well, these first two terms, the texture field differentiated with respect to theta and p hat, this can be simply obtained by backpropagation through the texture field. But how can we obtain the gradient of p hat, the optimal surface location with respect to theta? Remember, the optimal surface location depends on theta, because if I change the occupancy network parameters, then the surface changes. So of course, also the location will change. Now it turns out that we can find this gradient by applying the theorem of implicit differentiation to the level set constraint, which is the occupancy network at that surface location should be exactly the level set, this threshold tau, let's say 0.5, between 0 and 1, 0.5. And if you apply this here and we reformulate this slightly, we get this expression, which is an analytical solution to that gradient that we are interested in. And so we can then compute all the gradients now, and we can update the gradients. So this is illustrated here, where we have now modified with this gradient update, we have modified both the occupancy network that defines the shape and the texture field that defines the color. And the particularly nice thing about this kind of what we call differentiable volumetric rendering is that it has an analytic solution, so there's no need for storing any intermediate results as in voxel-based rendering, where you have to store intermediate results and backpropagate to all the voxels along the ray. This is not happening here, and it's still working, which is kind of surprising, because the neural network has intrinsic smoothness properties and propagates information automatically, if you will, into its neighborhood inside the volume. Right? So because of the smoothness properties of the neural network, we just need to differentiate at the surface and then basically update the parameters that we get from there. Yeah, so this is some results. So here we have, the task is the same as before, right? So we have now used this differentiable renderer to train ShapeNet models on many objects, several categories, where now the task is at test time for an unseen image to predict a 3D shape or a texture 3D shape. So what you see here is just the inference result. And so here's some baseline. This is a 2D supervised baseline, a 3D supervised baseline, and this is our reconstruction. This is a particularly hard example also because it's very textureless. And what we can also do is we can use 2.5D supervision. So we cannot just use RGB, but we can use RGB and depth. It's easy to integrate into this formulation. Here's another example with a car. Now, of course, using this for training a model works only when you have enough data, and in reality, there is not a lot of data that we can, at least not across the same category, that we could use. So we have also tried to use this model for overfitting, where we take this model, just to demonstrate it also works in real data. We take this model, overfit it on a DTU data set, just a single scene, similar to how NERF overfits to a single scene. These are the results that we get. And you can see, well, there's some viewpoints that are unobserved, so you get some artifacts, but in general, you get quite nice and watertight reconstructions demonstrating that this gradient updates of this implicit function through just image information is actually working. Yes, and I have to mention, there's a nice also follow-up work from Jaron Lippmann's group called IDR that extends this to view-dependent appearance, which is actually quite important for the DTU dataset because it's not Lambertian, so you get quite a bit better results if you model also view-dependent appearance, and it's the standard today. Then, well, we're trying to go further and relax assumptions further. So what we are now trying to relax is, well, in the previous model, in this one here, we have assumed that the camera poses are known. So we have first ran a call map structure for motion pipeline to get the camera poses, and then from the images, we can do the reconstruction. But what if we even don't know the camera poses? Can we also do something? And this led us to graph generative radiance fields, which is using a different representation. It's using the NERF representation, a radiance field representation. So instead of predicting occupancy and texture, here we're predicting color and density. They are quite related, and we have a very recent work that combines the two representations. They can actually be combined, but this is using the plain radiance field representation that has also been used by NERF. So if you will, it's a generative model for NERF that from an unstructured image collection of a particular object category learns a generative model of that collection, but not in 2D, but in 3D space. And so we have this conditional radiance field here, this G, that takes an appearance and a shape code that's randomly sampled from some distribution, some latent distribution. And then it takes this K indicates the camera intrinsics, and it takes the camera pose and some dilation pattern, because we can't do, this is very time and memory intensive, so we can't do this for the entire image. So we're just predicting patches. It's a patch-based model, patch-based GAN. So we're trying to predict for a sampled patch the values for each pixel in that patch, and this is illustrated here. And then we're sampling the same or similar patches from real images, and then we have a discriminator that works only on these 32 by 32 pixel patches in order to make this actually feasible. But otherwise it's very, very similar. So this part here, this volume rendering, is similar to NERF. And then the surprising thing for us was that it actually, we could get it to work quite well. So here are some results. These are early results. We have quite a bit better results now, but these are early results that we have produced for the paper, where we have generated images from cars. This is from the Kala simulator. We have generated a lot of images from cars, and then just from these RGB images, without any pose information, the model is capable of extracting a 3D model, which we can afterwards manipulate, where we can manipulate the pose, the viewpoint, the shape, and the texture of the objects, as you can see here, and automatically has established, in order to be able to do so, because we force it through this 3D process, this image formation process, it must automatically establish also geometry, which you can see at the bottom, but geometry hasn't been used as an input. And so here are some examples on Salabay as well. So we believe that, you know, lifting these 2D models to these 2D generative models to 3D is actually quite important if we want to go further in scene representations in the future. But of course, we are not yet at the level of fidelity that we can have with 2D generative models. So there's still work to be done. One rather recent work that we're going to present at the upcoming CVPR is Giraffe, which is basically an extension of Graph now to compositional scenes. So we're relaxing even further here. We are saying, well, what if the scenes that we are looking at don't just comprise a single object, which was the assumption before, but it could comprise multiple objects. And what if we wanted to disentangle these objects, the foreground from the background, for instance? So here's an example where we have a shape and appearance code for a particular car, and then shape and appearance code for the background. And then we have the pose for both, and we combine this. And because it's very natural to combine this in this radiance field formulation, it's just these individual components just define subvolumes, so we can combine them. Then we can train this entire thing in order to produce image outputs. And what we have done here is we are not using radiance field, but this is why it's called feature field. We are predicting features in the dense volume, and then we have these features mapped using this volumetric rendering process into a feature image, and then this feature image is decoded using a 2D decoder using this generative decoder into the image that we're interested in the end. So here's some results of this. Let me look at the time. Where you can see some comparison against 2D based GANs first. For 2D based GANs, we can't get the same level of controllability because it's not able to disentangle all the aspects. So you can see if you move in one particular dimension of the latent space, if you translate an object, then also other aspects of the scene get modified on this simple clever data set. But here, in contrast, in our approach, we can modify, for instance, translate each object individually without affecting any of the other objects. But both of these models have been trained in the same setup, so both are trained just from images. And we can do things like rotating objects or changing the background, so things that a standard classical 2D GAN is not able to disentangle. We can also add more objects that have been observed during training time. So here, this was trained on 2 object scenes, and we have added more objects at test time because we can just composite them. And here's some examples on controllable scene generation, where we rotate the objects in space, we translate objects, and we can do this even beyond the bounds of beyond the distribution that was observed during training. So we can extrapolate a little bit as well. And here you can see some churches where we move the background, but keep the foreground intact. And you can see that the foreground and the background are disentangled to some degree. We can change the background appearance, which in this case also changes the foreground appearance, because it's, churches at night tend to look different than churches at daylight. And here's some out of distribution samples. So we move the objects further than they have been moved, or that then they appeared in the training sample. Yeah, okay. Now, very recent, this is not published yet, we have worked on Campari, which is yet trying to remove another assumption that we have. And the other assumption that I haven't told you before was that despite, we are not requiring we're not requiring the cameras to be known. What we require to be known is the approximate camera distribution. And if you get that wrong, it turns out that graph or PyGAN or HoloGAN, like all of these models, don't work really well. So there's a lot of engineering in all of these papers, we have to confess, that goes into specifying the parameters of the camera distribution. But it turns out you can actually also train the camera distribution. So here you see, for instance, this is the marginal distribution over elevation angles in degrees. And for a particular data set, and you can see the uniform distribution. This is what we use as a prior, how this gets deformed to the prediction here in green that is much closer to the ground truth. And this is really crucial. If you don't do this, then your generative model will will be contaminated with noise. The samples that you will sample will not just be from the wrong distribution, but they also will not look very good. And so with this idea, we hope we can alleviate a little bit this problem that these models have to be hand-tuned. Okay, so now let's move forward. Most of the examples that I've shown you so far are looking at relatively small scenes. And this is an inherent limitation of these implicit neural representations. There's two, actually. So here's a rough layout. So we have an input that's encoded into some feature vector, and then this feature vector is passed through an MLP. That's the occupancy network, right? So one limitation is that we have considered mostly a global latent code. So there's no local information here. It's leading to overly smooth geometry because of that, because we can't just not represent the entirety of all objects in the world. We're using a 128-dimensional vector. That's very difficult. And then we have a fully connected architecture here, which doesn't exploit things like translation equivariance that we are so familiar with and that are so useful in the context of maybe convolutional neural networks. So, and this is what the result of an occupancy network looks like. On the right is the ground truth, on the left is the prediction. If we don't give it a single object, but if we generate scenes with 4 or 5 objects each, as the ground is always the same, the ground is well reconstructed, but all of these objects are very poorly reconstructed compared to the reconstructions that I've shown you before. And this is exactly, the cause for this is exactly what I've just mentioned. So what we proposed here in this paper in ECCV is convolutional occupancy networks, where instead of this monolithic occupancy network here, we are trying to first, so we're combining the idea of convolutions with occupancy network, MLP, implicit representations, where we have this, first this encoder that encodes not into a global code, but encodes into a volume. Now, this is a discretized volume, but we can query the discretized volume, these features in this discretized volume, by using simple trilinear interpolation. And then we get features for a particular continuous location in the volume. And we can pass these features along with the position through that MLP that predicts the occupancy probability. And so we get a little bit the best of both worlds. And this actually leads to already much better reconstructions and even faster convergence, much faster convergence actually for a single object. So here's a comparison of occupancy network to this convolutional idea. But what it particularly enables is reconstruction of very large scenes. So we can apply this model then in a fully convolutional manner. So we can, because it's translation equivariant now, we can slide it through this 3D volume, because the entire 3D volume here in this case wouldn't fit into memory, and then reconstruct things like Matterport 3D. And here's some examples of what this looks like. So it's really, for implicit representations, it's really comparably large scenes that we are able to reconstruct with this model, and it's not too slow. It runs in a few minutes. So we get these nice reconstructions out. So this was reconstruction from a sparse and noisy point cloud. Okay, and finally, before I want to conclude, I want to show you some of the current research directions that we're doing in this field. Kind of this field of implicit or coordinate-based representations has exploded over the last 1.5 years, and these representations are becoming relevant for more and more applications, going far beyond just plain reconstruction. So here are some examples, and these are examples from our research group, but there's many more from other groups in this space. So one thing that we have recently done, and the paper I think just appeared archive today, it's called Unisurf. It's, as I mentioned before, there's this connection between the radiance field representation in NeRF and the implicit surface representation, and both of their disadvantages and advantages. And we have a combined mathematical formulation for both of them. And the nice thing about this is that if you use this combined formulation, you can do things that weren't possible before. So one limitation of implicit surface representations, like the DVR approach, was that in order to reconstruct from images alone, it was always requiring object masks, pixel-aligned object masks. which is often not mentioned, and also I didn't mention it in this talk yet. And it's often assumed in many of the reconstruction methods, but it's a fundamental limitation because you have to really find the outline of the object, and then some scenes they don't have single objects, right? So for those, reconstruction then fails, or frequently fails. So here's an example where you can see like one of the best possible reconstructions that we have obtained. So we really cherry pick on the baseline here of a model, and it was only possible for this particular example here because the background was black, of reconstructing using the surface-based representation. Now this volume representation, this volume rendering representation as NERF uses it, can reconstruct this type of scenes without masks, but if you extract the geometry from there, because the geometry is not the primary goal of this approach, but the primary goal is to reconstruct appearance very well, novel views. If you extract the geometry from there, you get a lot of noise, and no matter how you set the threshold, either you're not reconstructing the object anymore, or you're getting just a lot of noise. And so with this unified formulation, we can get kind of the best of both worlds. We can get a good reconstruction without input masks. That was the goal of this project. Another thing that is a limiting factor of these representations, why they are not, in this case NERF, why they are not directly applicable to applications like VR and augmented reality, is that they are not, the rendering is still not real time. Right, and of course, if you want to apply that, it must run real time, ideally even on a memory constrained and compute constrained device. And what we have proposed in KiloNERF is a model that can render 2 to 3 orders of magnitude faster than NERF, but it renders with the same or even a slightly better quality. And it turns out that this is possible by just not, instead of using a single big MLP, to use many little tiny MLPs that can be trained using a student-teacher process. That actually works quite well. And there's actually a lot of interest in this particular research area. So since we have starting working on this, there's at least 3 or 4 other papers that have tackled similar problems, trying to make these representations faster for rendering, for instance, in the context of virtual reality. The representations have also been recently used more and more for reconstructing human body models. They can be used, for instance, as in the context of predicting offsets from a simple body mesh, or they can be used to directly predict the shape of the body. And what we have done here is called SNARF. There's also preprint out, is that we have tried to predict an implicit 3D model, but also at the same time learn the skinning weights, the forward skinning weights. And while this is not easy to optimize, it turns out you can actually optimize this also using implicit differentiation, and you get a model, because we have this skinning weight model that is very, very good inside our model. We can get a model that basically generalizes very well to unseen poses. So here are some extreme poses that haven't been part of the training set and where a plain occupancy network would horribly fail. Or not use good skinning model, but here in this combined approach with skinning models and implicit representations, we get also these very challenging and unseen poses. Another project that we did, and that is already, well, it's going to be published, accepted to CVPR 21. It's called SMD nets, ultra high resolution stereo. And here the idea is that we can overcome some of the fundamental problems in stereo, low-level stereo vision, also using this idea of coordinate-based prediction. For instance, we have a model here on the bottom. You can see a standard state-of-the-art stereo model for a particular scene. This is a disparity map, and you can see that it's bleeding into the background, and of course that it only predicts at a particular resolution, while our model has a sharp boundary. It's really sharp. There is no bleeding. If you would look at the point cloud of this, you wouldn't see any border bleeding. And at the same time, it can you can query it at and you can also train it at arbitrary resolution. So the precision basically only depends on the capacity of the model, and of course also on the input images, the size of the input images that you use. And finally, these representations are also more and more interesting in the context of robotic applications. So here's one where it's called NEAT, that we have recently worked on, where we're using these implicit representations in combination with attention maps to predict waypoints continuously. So this is the continuous part. So we're predicting them continuously in space, and we're predicting continuous semantics for self-driving on Kala. And it turns out that this is one of the best performing Kala methods on the Kala leaderboard currently. And in particular, it drives very safely. It has a very low infraction rate and very low chance of running over pedestrians. And I want to briefly show you this video. Offsets to future waypoints, which are color-coded here. This triangle indicates the observer, and here in red we indicate the predicted waypoints. And then the bird's eye view semantics, that's auxiliary supervision. We use that and quite a bit. Traffic lights here in red. Cities in Kala. Some of these cities are more downstream than others, but all of them are quite dense in the newest Kala versions, with a lot of traffic, a lot of pedestrians, very challenging scenes. There's puddles on the ground. There's traffic lights that we have to adhere to. And sometimes there's turnarounds. There's multi-lane traffic. Here's a complicated intersection, for instance, and the model that you see here is trained end-to-end, right? It's an end-to-end trained model. It's not a model of pipeline, but it's trained end-to-end for this driving task. I think it's quite impressive progress that the community has made in order to get end-to-end driving work better, at least in simulation. But I believe it will also play a role in developing self-driving cars that will be on the road. Okay, so let me stop here and summarize briefly. I've talked about neural implicit models, coordinate-based representations, sometimes called, that I hope to convince you are an effective output representation for shape, appearance, material, and motion. They don't require any discretization and model arbitrary topology, and they can be learned from images via differentiable rendering. There's many applications, 3D reconstruction, but many more that I've just shown. However, well, geometry is not explicit. They must be extracted in a post-processing step. But in some cases, for instance, for self-driving, we don't even need to extract everywhere. Or in robotics, maybe we don't need to query geometry everywhere. We can query adaptively. And then these models are really fast. Querying a single point is super fast. Extension to 4D is not straightforward. And the fully connected architecture and global conditioning lead to overly smooth results. But there's some promising directions here. So for instance, local features, conv-onet, or PyFu, which uses projections of the 3D points into the image domain, where you get local features from the image, and better input encodings, which are now also omnipresent, like what NERF is using, can also be used, of course, for coordinate-based surface representations. That's it from my side. I'm happy to discuss and hear your questions. Thanks.
Thanks a lot for the cool talk. Maybe we can start with one question on YouTube, which is how we can potentially use these implicit functions or representations to extend to general reconstruction from single images. They say on RGB data sets like Pix3D or Scan2CAD, or do these currently contain too many different objects? And what are your thoughts on retrieving CAD models versus predicting implicit representations?
So the last part, this was a long question. The last part was the important bit, CAD models versus like retrieval versus prediction.
Yeah, so last part was retrieval versus prediction. Then generally, can we use implicit representations as they are for large complex scenes in reconstruction from a single image?
Yeah, that's a good question. So I guess, the reconstruction from a single image I have demonstrated extensively here, but maybe the question is how to go forward towards scenes also from a single image. And so I believe like these representations, in particular now with the last couple of months seeing better and better representations that also able to reconstruct appearance and better generative models, are nice in a way that you can take assets or data from everywhere. Could be scans, could be like CAD models, and distill them in a sense into nice little generative models per object. And I think the compositionality has to be taken into account if you go towards larger scenes. But and there's some first approaches. We have also this, what I've showed here, the giraffe model. Of course, this was in a very challenging setup without making any assumptions. But now assume you have available some annotations. Let's say you have a good instance segmentation algorithm. Then you can build per category models that you then can composite together. And I think in combination, in particular with better and faster rendering techniques that run faster, this is very promising. So I think the future will be compositional. So we will have to build models that somehow separate the scene into their individual parts. Also because not only because it's easier to compress and to learn, but also because we might want to do something with these environments. We might want to interact with these objects. We might want to model physics, etc. So yes, I think that's probably the way to go. And we have focused a lot on as little supervision as possible, but I believe there's some supervision available. Of course, there is good instance detectors, there is good single image depth predictors. So why not using them for building these scene representations? Yeah.
Shall I ask a question?
Happy to.
Okay, good. Yeah, thanks for the talk. It's really very super impressive as usual, and it's very very nice pieces of work. So two question areas. So the first one is can you speak a bit more about the downside of this development and this representation? I mean, first of all, compared to isn't it worth to have some form of explicit knowledge like parametric models where you know it's already it's a flat wall or something like this, right? That you've got some. Is it worth to mix it with some more traditional models, or is it really completely, you think there will be completely abandoned these traditional models? And are there some downsides? It's sure, like it's great to push all of this, but what you see also going back to the old representations, is that completely obsolete or not?
Right. That's a good question. So I think like one downside at the moment is particular for training. I mean, first of all, like while inferences now can be done faster for some of these models, it still requires a distillation process that might be slow, and it's still not fully configurable in real time, right? As some of the if you think about Unreal or the latest NVIDIA teaser videos where you can have games and reality that's real time and photorealistic, right? So, and these are using traditional representations, not implicit representations. And so there's something to overcome here, but then in particular also training is super slow in many cases. So if you're, for instance, looking at the nerve models or looking at this here, like these models, they train for 2 days for a single scene, right? So that is something that is really problematic if you want to scale them up and train them on very large scenes and very many objects. And then in terms of representations, I fully agree. So there are some representations that are difficult, and you have mentioned one. Plane is a representation that's very easy to represent parametrically, but it's hard to, well, it's not hard. It's possible to represent implicitly, but it's kind of overkill because you're using a high capacity model to represent a plane. And again, I think we still want to have compositional models, and compositional models could include both. But even then, if you think about planes, a plane by itself is for reconstruction is also not a very useful primitive unless you combine it with some with a shape, right? So you need to specify how the plane is delimited. And so maybe in 2D on the plane surface, you still want to define a function, and that function could be represented using an implicit model, for instance, right? Like we, for instance, represent in 2.5D stereo using these approaches. Yeah, and then maybe other downsides, of course, I mean, it's implicit, so you don't get the mesh directly, so it's not directly compatible with rendering pipelines, but I believe that there's more and more rendering pipelines that will be using this type of representations coming up, and so that might not be a problem in the future, but you need to do clever things, right? So if you have a very large scene, you need to do still clever occlusion checks. You can't just query samples along the ray up to 1 kilometer. I mean, that's certainly not scale, right? While in the classical, like with classical primitives that people use for rendering, these problems have been overcome already. So there's still some way to go here. Yeah, and then, yeah, I don't know. Yeah.
Okay. So yeah. The second question I have is, did you like interpret or look more closely at the networks? For instance, I mean, texture is very different to shape. I mean, so neural networks are smooth implicitly. Hence, this is good for quite often for 3D shape, but texture, I mean, some of the textures were rather smooth.
Right.
Not so many details. I mean, the networks for represented texture and versus shape should be quite different, right? And can you
that's true.
And so is it, that's one question, but also, did you look at the networks? The other thing I was wondering was shape. I mean, because the way you query it, you always get a watertight surface, but there could be potentially, even in the 3D, if it's not, there could be some islands or something like this, but you've never seen these or something like this. Did you look at the networks? Did they like overfit, or they have some weird behavior, but you never seen this probably, or like, that's a question, do you analyze these networks?
Yes, that's a good question. I think that's actually something we're currently very much interested. So to the first part, yes, texture and geometry need to be represented differently. Also, texture itself or appearance itself has different types of representations that we're using. So for instance, the view-dependent part needs low capacity, and the albedo part needs high capacity. And this is something that we integrate into the networks. So for instance, the view dependency you can inject at a later point in the neural as a condition in the network, and so you can force it to have lower capacity. And then for the geometry and for the texture, we're using now these Fourier features to get higher frequencies, because they are otherwise overly smooth, and that is true. It's particularly harmful for texture, but then also if you have complex geometry. And then there's different ways to regularize this. Again, you can build different architectures that have different capacity for different things that you're predicting. You can also, what we do, for instance, for the KiloNerve project is we are using, like if you have too much capacity for some of the parts of the model, then you see artifacts. That's true, and we are regularizing using weight decay. So you can also use standard neural network regularization techniques to regularize only the aspects of the model that you're interested in. But it's not a fully resolved question, I have to say. So there's a lot of, with this capacity is really important, and handling it right for the different aspects that you're predicting, like geometry, texture, view dependency. But there's no golden, no holy grail yet. So we still need to come up with more principled solutions on how to do that. And also the architecture itself, there's different ways you can use different activation functions. There's Siren, for instance, using sinusoidals. There's people using ReLUs. We use a lot of standard MLP ReLUs, and I think there's trade-offs. Some of them give you slightly better results, but are more brittle. They more easily get stuck during optimization. They need to have a very good initialization in terms of geometry, some of them. So there's these trade-offs. And what was the second part of the question?
Oh, that was both parts already of the question.
Okay.
So,
Yeah.
yeah.
Yeah, so that's important actually, yeah, because you now just using a plain MLP and giving it a lot of capacity and hoping it will do well doesn't work well. You will get the network will hallucinate artifacts in spaces where if you look from novel viewpoints, you can see this. For instance, if you look at the geometry here, you can also see some artifacts in the geometry. You can see this. And currently we have one project where we're looking into how we can generalize with these models. And it turns out that this regularization is super important, because if you have these Fourier features and you look outside of your training domain, it will do all kinds of weird things. And so you need to really properly regularize that.
So you do a lot of sorry, I've asked a lot of questions, but last one, do you do a lot of generation to also analyze these models and see where they fail?
Yeah, we do that, but we also try to get a little bit more theoretical insights, but it's not so easy. Yeah, but we are I mean, we're doing a lot of visualizations. Yeah. Okay. Also in 2D, it's very instructive to do this, to apply these models in 2D, not directly go to 3D space, because in 2D you can see the level sets much better, right? You can visualize what's missing here. You can visualize the level sets. Yeah.
Okay. Thanks. That's like most of my questions. Sorry.
Thanks, Carsten. Yeah.
Cool. Actually, in terms of this kind of analysis, I think the nice thing about this convolutional occupancy network formulation is that you hope that you end up with an implicitly learned kind of part decomposition, where similar kind of grid cells end up closer together in the latent space. Is that actually what you observe here? And do you think you can kind of, in the extreme, like end up learning something like a scene representation that implicitly decomposes into, I mean, obviously you would like to have a nice instant segmentation and stuff like this, but can you maybe get this just by learning on scenes with shared kind of common objects?
That's true. It's actually, this is a very good point. We haven't looked at this too much yet, but in theory, if you have a fully equivariant model, right, you could, in theory, if the data set is big enough, you could convolve this over the entire world and ideally get regularization effects, because it's equivariant. So if you have similar inputs at one location of the world, you have of the building, you have similar features at another location of the building, then the output should be similar. And so if there's different noise characteristics in the observations on both sides, then they can cancel each other. That's what one would hope. But we haven't had time to very carefully investigate it. Of course, in terms of decomposition, maybe it gives you good features, but the decomposition is still like not ideal, I would say, because it would, if you just operate at the voxel level, then it will not naturally decompose or segment objects well. But maybe, and there was a very recent paper I've seen on Archive recently, where they looked into these type of representations and found, I think it was for generative models, and found that if you look at the representations, then you can then the generative model has already learned useful features for semantic segmentation, where you can, I think you also have some work in that domain actually, right? Where you can then train just with a few annotated examples, and it will give you a very nice segmentation of larger scenes. So I believe that's also happening here, and that will probably be, that property will probably be stronger for these convolutional models, because they share this information.
Yeah, no, but theoretically, it would be interesting to see whether that's actually possible with without any explicit translational invariance. but yeah, I think this is what we're all looking for, is generalizability and better use of shared regularizations.
Right.
Like regarding this room or like house scale reconstruction, have you looked into some kind of completion? I mean, like in this, basically in this feature space?
Yeah, we have some experiments with completion, I think, in the paper. Yeah, so that's the natural experiment to do, I guess, right? So here, I guess what you're referring to is that the scenes are not complete that we reconstruct. I think for this particular example, we haven't trained for completion. I don't know by heart. But yes, so there's also this also I think from Theo Minnick, this nice line of works where you artificially destroy. I mean, of course, the problem with this data set is that it's not complete because the scans are not complete. But you can artificially destroy some of you can create a learning task by artificially removing some parts and then trying to predict those, and then hoping that the model generalizes. From there, generalizes also to complete parts that are not even in the ground truth. And I think that should work similarly here. I don't see, I mean, it's conceptually, it's not different. It's just a different representation. So I would believe, but we have considered this not, we did not consider this. We have considered only the completion problems only in the context of fully supervised training, where we assumed like synthetic scenes where all the ground truth, the complete ground truth was basically available.
Yeah. I mean, one more general like note, like I mean, like we talked about like classical representations. I mean, like these implicit representations are also classic, right? And I mean, we have a lot of like work like these radial basis function networks and stuff like this. So that's probably older than I am old. So so that's I mean, the new part is that we have like these deep neural networks that store these.
Exactly. So it's the same story as for reinforcement learning or anything, right? So now we have basically we can show that this works also with deeper models. So I have to say the classical implicit models, so there's the level set models that haven't used learning much, right? And then there's the discrete implicit models that use like voxels, large, I mean, these are the most prominent ones at least, right? So using a neural network as this representation, and of course this was also possible just with the advent of these techniques of conditioning these networks well and so on, right? So one led to the other, I guess. Yeah, but it's a good point. It's not like these ideas have been all around for 30 years.
Yeah. I mean, especially like if you have like these radial basis function networks, I mean, that's already, I mean, it's not a deep network, but still, I mean, the idea is already there. And especially if you compare it to works like Sirens or so, which basically optimize for a specific scene, then it's exactly like the same line of work with other
this
functions.
paper is something that we discovered after we have done this occupancy network paper. So we weren't aware of that, but it's kind of natural that people that look into support vector machines, there were also, the community was smaller, but there were also people interested in 3D, and it's super natural to consider this as a classification problem.
I mean, I find it interesting that there are now like combinations of like these radial basis functions and implicit functions to have like local implicit functions basically, and you use radial basis functions to blend between different implicit functions. So somehow we now build hybrids of known techniques, and now
seems
these
like a good thing to try. That's true. Yeah.
I mean, the same is like for these convolutional occupancy networks. I mean, now you have like basically you end up with a grid structure, and in this grid structure you have features, and these basically give you then access to your implicit function, and that's the same for these IF nets. And so it's some kind, like we are now searching for hybrids and finding out what is the best combination, and like especially like these more localized models, they show basically promising results in details, and so that's kind of interesting. Or also like these like only based on points where you have implicit functions embedded on points or on bones, like the work that Sharad Pons-Moll is doing. So that's quite interesting, I think.
Yeah, I also, maybe my advertisement for this type of models was a bit too strong. So of course there's downsides and there's value in other representations, but I think what's nice is that they are kind of elegant in the sense that they can handle these topology changes, and they can utilize machine learning in a very effective way. And now, since we have more data and more compute, I guess that's the right time to look into these models. But they're certainly not the right representation for all things. In particular, if I think about doing things on memory and compute constrained devices like mobile phones, I would probably not use this type of models at the moment, at least. Yeah. Cool. Thanks, Justus.
Maybe one last question from YouTube, and I think we touched on a few parts of this, but not maybe exactly this direction. So what do you think are the most promising directions of creating representations of scenes that have some kind of hierarchical decomposition? So is that happening at like the object level or the part level, such that you can incorporate these neural implicit representations?
That's a good question. So we have I think it's hard to answer. So we have one tricky aspect of this is like how much supervision do you want to use, and how does the world decompose without having a lot of supervision? So one project that we did is this recently is this neural parts project. Where we have parts of neural representations. These are also occupancy representations that are connected through invertible neural networks, actually. And the nice thing about this is that they are completely unsupervised. This is a upcoming CVPR paper I didn't have time to talk about. Should probably have included it. As you can see, of course, because it's completely unsupervised, the part decomposition seems to be sometimes a little bit arbitrary, but in general, it gets the majority of the, it gets a semantics that we feel is somewhat familiar to, or seems to be sensible. So here are some comparisons to, previous versions of this model that we have using superquadrics and, CVXNet, which is very popular, and our representation. So here, I think if we talk about articulated objects like humans, we definitely want to go to the part level if we want to understand them at the part level. But if we don't want to understand them at the part level, it's not necessary. And so we can maybe use a more coarse-grained representation. And that the objects in like indoor and outdoor scenes, sometimes it's even not clear what is constituting an object. We have been developing this Kitty 360 data set recently, and as like the successor of the Kitty data set. And there we have semantic annotations everywhere in the scene. And it turns out for some semantic classes, so we tried to, for instance, create semantic annotations and instance annotations for trees and vegetation. But it turns out there's a continuous transition between vegetation and trees and buildings, because vegetation can be on buildings, it can be compact, it can be very dispersed, it can be, there's just it's sometimes very hard to specify as a human what actually the representation should be. And then even if we could do that, we would need to annotate all of the data. So for me, it's a little bit about like, what do we have? I mean, I think we should first ask, what do we have as supervision, and then what problem do we actually want to solve? And if it's for instance, if it's self-driving, then some of the objects like cars, they can be represented without parts, because the parts are not necessary, I believe, the parts of the cars, the other cars in the scene are not super necessary for doing a good job in self-driving. Yeah.
Cool. Yeah, makes sense. All right. I think thanks again for the great talk. Sorry about the technical issues at the beginning, but I think we had a nice discussion. And then thank you, Justus and Karsten, for a great panel discussion.